All right. So this is lecture 20, 24th of February. And let's pause and see where we are. So as before, let me kind of quickly over review where what we've been doing has been equilibrium analysis of rigid body structures, and we covered frames and machines. We spent a few days, we did quite a few problems. Now we're going to go to the second and the last type of structure that we want to study, and those are trusses. Um, I will spend a few days on this, but before doing that, let me remind you that in the syllabus, I have referred to a course, which I'm going to send it by chat here. Sorry about that. Here it is. I just made a wrong copy. Ignore that one. So I would send you that course, and I highly recommend for those of you, especially that you want to see a lot more examples and get a very good grasp of this concept, which of course I'm going to spend a few days covering in this class also. That's a very popular course, which is focused on truss analysis, and you really get good at it. I've had lots of good feedback, and lots of people have taken that. So that's an extra resource if you're interested. But let's getting back to trusses and what they are. Trusses, I always start by saying that, are those kind of structures that their characteristics violate the characteristics that the frames are known for. What do I mean by that? First of all, I don't know if you've seen any truss structures. I'm sure you've seen at least some roof trusses which look like this. Okay, those of you, especially if you've done some construction work, you've gone over a bridge that probably you've gone over a bridge. You've noticed that looks like this. It is a structure like this. Okay, cars travel here or travel here. So what is a truss structure? Okay. In fact, there is also a very good truss picture in your book. Maybe I'll also show you that one because it's a really beautiful truss structure that let me find it here. I'll show you. It's on the beginning of the section. Okay. See, this is a roof truss. You can see that, right? And there is another picture. There's another example of a truss structure. In fact, you've seen cranes. Cranes, you've seen in, they're on the construction sites, there are trusses. And this is another one, truss structure, which is a bridge. So what is it that describes a truss? Trusses are structures that, number one, all members are two-force members. Remember what was the definition of a two-force member? Members that are only connected at the two ends, no load is carried by that member, and the two ends are pin connected. So in all trusses, all these joints that connect all these members to each other are pin connection, and we assume that these structures are not capable of carrying load along any member. In other words, you cannot have loads here or load here. Okay, what does that mean? because you're going to ask, you know, how could that happen? Because if it's a roof truss, you have loads all over the roof, snow or people walking on it or whatever. So you don't have just loads here. This is an assumption we make that these members are designed or the structure is designed to only carry loads at the joint. So if you have distributed load like that, for the purpose of designing this structure, we find equivalent of these loads and put them at these joints, okay? So even if you have traffic going over this bridge, we assume that these traffic loads are generating forces that we can assume equivalent load would be acting at these joints. That's the meaning of only forces acting at the joint. So all members are two-force members. No load along a member. They're only connected at two ends, and these ends are pin connection. So when I say they're all two-force members, inherently and implicitly, you're saying that loads act only at the joints and all joints are pin connected. Okay? Bolts or rivets, no welding. Okay? So what is the objective? What is the objective of studying these structures? Similar to frames, the key objective is what? We want to find forces in each member. You remember, in a frame, we wanted to find all forces that are acting at the joints where these members were connected. Same thing here. But the forces in the truss, these are two force members, only act at the joint. So that's what we want to find out. Forces that act internally at each joint. But remember, if you have, this is a truss, let's say these three members are coming to that joint, okay? Forces that are acting at that joint means these are the forces that are coming from the corresponding members that are two-force members. So that means you had a two-force member here, a two-force member here, that is causing a force on these joints. So that's what we want to find. However, in order to do that, we need to categorize truss problems in two broad categories. Sometimes you want to design a truss. In that case, you will need to know the force that each member is subjected to because you want to choose the material, size of the member, and so on. So you need to know how much force every single member carries so that you can put all that truss together. That's one type of problem. The second type of problem is you have an existing truss, but you want to only repair a few members. That is, you want to just, okay, this member is broken or corroded or these two, and I only want to replace these two. I don't need to find how much force every single member in this truss, existing truss, carries. I only need these two. Okay? So depending on what kind of problem you're facing, there are two approaches for designing a truss that is finding all member forces. We use an approach called method of joints. If you only want to find member forces in a few members, this is for a truss that doesn't exist, you want to design. So you want to find what force every member carries. This is for an existing structure that you only want to find forces in a few members. We use a method called method of sections. Okay, so we will cover both, and that those both are covered in the course that I've referred to. Okay, and I will start with the first one. What are the tools that we use? Equilibrium equations. So that is our tool, equilibrium equations. In the case of A, which is method of joints, okay, this is what we do. Similar to frames, I always strongly encourage following a methodical approach. So for the case of trusses, what is that methodical, a step-by-step approach that I mentioned in frames? In that online course, if you go and take that, you see that I've referred to 7 easy steps to solve a truss problem. Here, I'm consolidating some of those steps because we don't have time to cover all these in 3-4 days. So I'll make it sort of simplify that. What are these steps? Step number 1, similar to frame, you establish an X and Y coordinate system. Step number 2, this is very, very important. Let me first set up a truss, show you a truss structure, draw a truss structure, okay? Let's say you have a truss like this, externally supported, okay? So you have, okay, all these members, okay? So you have a structure like this, subjected to this load of 30 kilonewton here, 20 kilonewton here. Let me label that A, B, C, D, E, F, G, H, I. So this is a truss. How many members? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14 members, right? Remember, 14 members. How do you start? As I said, the objective is you want to find forces in every member or forces at every joint when you take members apart, similar to frame, that you took all the members apart. But the steps are as follows. After you draw the XY coordinate, this is the next and crucial step. You look at this truss and identify, okay, joints with these 3, okay, characteristics or properties. That is, what are those? A, okay, only 3 forces come to that joint. Condition number 1. B, 2 of those forces are collinear. Okay? All right. If these 2 conditions are satisfied, okay, the third force has to be 0. What does that mean? If these conditions are satisfied, the third force, which is a force in a member, has to be 0. If the force in that member is 0, we call that a 0 force member. 0 force member, ZFM. So what's the big deal? Let me show you what the big deal is. If for that loading and let me emphasize, these conditions are only a function of the type of loading you have on a truss, right? Because depending on what the external loads are and where they are acting, you may or may not have a member that carries no load. It's for any given loading condition. So let's see what that means. That means if you have a member that carries no load, that is 0 force member, you can remove that. You remove that. Okay? So condition number 2 is you identify these, and once you see a 0 force member, you would remove the 0 force member. So this is step number 3. Let's see what that means. So I'm going to look at, so when you remove that, then number of members is going to be reduced. So you don't have to find forces in all those members, or you don't have to consider the equilibrium of every single joint, because some of these members coming to that joint have disappeared. Let's look at this truss and look at these conditions that I have said here. How many joints you see that only 3 forces come to that joint? I see this one external, 2 member. This one, right? Here you have 1, 2, 3, 4. You have 1, 2, 3, 4, 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, 1, 2, 3 here. So that also satisfies. Do you see any other joint that only 3 forces come to that joint?
At point E, I think.
Yes. Good observation. Your name is what?
Sean Thompson.
Don Thompson.
Sean, sorry.
Oh, sorry, Sean Thompson. You know, Sean, you got yourself 5 bonus points that I'm going to record. You can use it towards anything you want. Why? Because Sean made a very important observation that I always emphasize to the students, that when you are doing this, don't just look at what you have inside the structure. This condition may be happening at a support as well, which is the case here. Why? Because this support represents 1 force, right? So at this joint, you also have only 3 forces coming to that joint. Okay? Now pause again and see at which one of these joints you have the second condition satisfied. That is, 2 of those forces are collinear. Because if you find 2 forces are collinear, the third force is the one that is 0. Look at here. These 2 are collinear. So this one is a 0 force member that I can simply remove that as if this member didn't exist. Why is that? Let me show you in general. Let's say you have a joint here and 3 members, 3 forces act at that joint, okay? 2 are collinear. This one is not, right? So what happens? If you have only these 3 forces at that joint, if I consider this as the x-axis, this as my y-axis, what happens? If this is a force F, I write summation of forces along y equal to 0. F has to be 0. And that's why I say, if you have 3 forces, as long as 2 are collinear, third one cannot exist. That means this member is useless. Remove it. Same thing here. 3 forces, 2 collinear. That means I can remove this. And you know what happens after I remove this? Something even more interesting happens. Wait a minute, I've removed this, and now I see a new joint where I have only 3 forces and 2 are collinear, and that is joint I, right? So that means this is going to be 0 as well. So once I remove that, do you see any other joint with that condition, satisfying those conditions?
Joint C.
Joint C. Now I have a joint very much like before, only 3 forces, 2 are collinear. So this doesn't exist. So you see, I started. So that means if these don't exist, it is pretty much like we didn't have these members, right? So this truss is consists of only this member, because these two are gone, okay? And this member, obviously, this member, and this is gone, so this member, okay? How about here? 3 forces, 2 collinear. So this one doesn't exist, right? So I have only one member here. And of course, this external load. So a truss.
Removed C, why didn't you also like do that at H? The like
Oh,
start.
yeah. Oh, wait a minute. No. You have
Oh, because of the other force.
Yes,
Never mind.
yes, that's right. So you see, we started with 14 members that you were expected to find all the forces in, but now you have ended up with 1, 2, 3, 4, 5, 6. You eliminated 8 members. So the truss problem becomes easier. That is why this step is critical, is essential. It is a must that you need to detect 0 force members to begin with. So what is the next step? Once you identify that zero force members, okay, and you know how many members you have, right? You go to the next step, step number 4. What is the step number 4? You start with a joint that has minimum number of unknowns. Okay? Solve for those unknowns, then move to the next joint, with minimum unknowns. So let's see how we are going to do this. So I'm going to look at this truss, okay? So I have these members, right? It's the truss with these members. Look at the joints. I have how many joints? This joint, this joint, this joint, this joint, and this joint, right? How many unknowns I have here? I have 2, because I haven't found the external force. So I have 2. These would be the same, but I haven't found it yet. So that's one joint. Here, 1, 2 unknowns. Here, 1, 2, 3. Here, 1, 2, 3, 4. And here, 1, 2, 3, 4. So I will start with a joint with minimum number of unknowns, and that is this one. So I'm going to start with A. Okay? Just about time. Coming in. Come on, 38 minutes after the hour. All right. So let's do that. So I'm going to look at the free body diagram of A. This is joint A. And this is the external force, 20 kilonewton. And this is F that comes from this member. Let me just call that member FAB. And this one, although this is the long member FAH, I call that F. Okay, call that FAH. Similar to what you were doing before for frames, you can assume any directions for these unknown forces coming to that joint, okay? But let me emphasize and re-emphasize. Remember where these forces are coming from. This force is coming from this member, because you've cut the member away from the joint. This member is exerting a force on this joint at that direction. So in other words, you have assumed that on member AB, you have a force like this at point A. And on member AH, you have a force in this direction at A. What does that mean? I said all members are two force members. That means the other member would be subjected to a force which is equal in magnitude, opposite in direction. In doing truss problems, for this reason, it is very important that not when you find these unknown forces, you make sure that what directions they're actually acting. And I show you why. So let's first solve the problem. First of all, the slope of this is given. Of course, I forgot to give you these dimensions, but they are given 2 meters, 2 meters, 2 meters, 2 meters, and this is 6 meters. So this is 6, this triangle, 6, this is 8. So this is 4, 3, 5. So in other words, the slope here is 4, 3, 5. So let's solve the problem. You look at joint A, you have two equations of equilibrium. Summation of forces along X, summation of forces along Y. Is a particle equilibrium. So you have two equations of equilibrium. I will start with summation of forces along Y. You can see by now why I'm doing that, because if I start with this one, I can immediately find this. Whereas if I write this one first, I will end up with two unknowns. So let's just start with this one. So I have FAH times 3/5 minus 20 is equal to 0. So FAH is 20 divided by 3. I'm sorry, 100 divided by 3, or FAH is going to be 33.33 kilonewton. But wait a minute, you're not done yet. That's the big difference between a frame structure and a truss structure. It is not just the answer that you find that is important, but since every member is a two-force member, you need to also recognize and detect whether that force, that member, corresponding member that is exerting this force on this joint is subjected to compression or being pulled away, and it is subjected to tension. Since the answer came out to be positive here, that means the assumed direction here was correct. These are then the direction that these forces act on this two-force member. And what are they doing? They're compressing it. So you need to put a letter C, meaning that this member is in compression. Why is that important? Because trusses are two force members. And depending on the material that they're made of, the strength or the capability of that member withstanding the force is different if it is tensile or compressive force. For instance, concrete is poor in tension, very strong in compression. Wood, very, very strong in tension, not as strong in compression. Okay? So you need to know if this member is in compression or tension, because the material that you're going to use makes a difference. Okay? So if the member is in compression, you want to use a very strong material, use concrete. If it's in tension, wood is fine. Okay? So anyway, so that's important that you need, otherwise you will be given only half the point for this answer. This is as important as the number that you find. Now you can solve for the other unknown. Summation of force along x is equal to 0. So I'll get negative FAB, negative 33.33 is equal to 0. Both are acting this way. So FAB comes out to be negative 33. Oh, wait a minute. This is the negative 33 times 4/5. And nobody was watching me, right? So it's 4/5 of 100 over 3. So it's going to be negative 26.7 kilonewton. So what we have learned so far, if you end up with a negative number, that means the assumed direction is wrong. That means force of member AB is actually acting this way on joint A. That means this member itself is subjected to a force that looks like this, and or since it's a two-force member, it is going to be like this. So this member is in tension. So get rid of that negative sign. You've corrected the direction. Put that tension right next to it. You may say, well, it's difficult or it's cumbersome or time-consuming. At each time I start to think about whether it is in tension or compression, right? I give you sort of a rule of thumb or a sort of a some way that you can quickly detect tension or compression and put it right next to it. Notice when the force of this member is acting on this joint in a way that this force is moving away from the joint, the corresponding member is in tension. If the force of the member comes towards the joint, member is in compression. So towards, compressive, away, tensile. Okay? Away means tensile. Towards means compressive. So if you remember this, you can quickly, once you solve the problem, you can find out. Let me pause here a little bit before I continue the problem. Any questions so far? No? So let's go to the next step. What have you done now? I solved for this member and this member. I said step number 4, you start with a joint with minimum number of unknowns. You solve for those unknowns, move to the next joint with minimum number of unknowns. So let's see how many we have here. This joint, I still have 1, 2, 3. This joint I have, this is known now, right? So I have only 1, 2. This one is still 1, 2, 3, 4. So I'm going to go with this guy, okay? Because I only have 2 unknowns. And now draw the free body diagram of that joint, which is joint H. I already know member AH was a compressive member, member in compression. So the force from that member is coming towards this joint. This is member FH, which we found it. That was 33.33. This is an applied load of 30 kilonewton. How about this member and this member? This is member, this is this member, HD, and this is this member, FHF. Again, you can assume any direction you want. Let's assume both of them are this way, okay? And now you have to write equations of equilibrium again, okay? To solve for these two unknowns. So I know the slope here, this was 435. I need to find the slope of this one. It's not difficult. How? In this triangle, you want basically this side and this side. This side is given is 2. How much is this one? I can easily find it from similarity of the triangle. Look at this triangle. Okay. And this large triangle. So if I need this, right? I call that X. X over, this is the corresponding triangle, which is similar to that. 6 is equal to 4 divided by 8. So that is 1, 2. So X comes out to be 3. So this is 3, 2, and this is square root of 13. So I have here 2, 3 square root 13. Okay, I need that because I want to write summation of forces along X. And as before, I need to resolve all these forces into their components, right? So this one is FHD, right? 2 over square root 13. This one is FHD, okay? 3 over square root 13, okay? Oops. Sunshine doesn't, okay? And this one is FHF times 3/5. This is FHF 4/5. Okay. Now that I have all those, okay, so get rid of these. So let's write equation of equilibrium. Starting with summation of forces along X is equal to 0. I have 30 minus 2 over square root 13 FHD minus 4/5 of FHF plus this one, plus, which is the force of AH, and that is 4/5 of F of AH, which was 100 over 3 equal to 0. Okay, so that's the first equation. Okay, so 4/5 of that minus 3/5, okay, minus 3/5 of HF. Let me see. This is 4F. So let me double check. 30, this is 2 over this. This one is 4/5, and this is 4/5. Okay, any questions here? So we need to simplify this. Okay, but let's first write the other equation. Summation of forces along Y. I have 3 fifth of f of h f. Okay. What else I have here? This one and this one. So I have minus 3 over square root 13 of FHD and minus 3/5 of that 100 over 3 is equal to 0. Okay. So I need just two equations, two unknowns. So let me solve for those two. I will simplify this. Okay, what is, let me simplify this. This is 0.6 f of hf. And let's see how much is 3 over square root 13. Okay, so let me square root 13 times 3. That's minus 0.83 f of hd is equal to 20. So what I will do, I will write f of hf is equal to 0.83 FHF, okay, plus 20 divided by 0.6, and substitute this now in that equation to find f of ht. So let me rewrite that. So I have 30 minus 2 over square root 13. So square root 13 inverse times 2, 0.55. So I have negative 0.55 FHD minus 0.8 times FHF, which is this, 0.83 FHF. I'm sorry, this is FHD, not FH. Okay, plus 20 divided by 0.6, okay, right, plus 4/5 times this, that is 26.7 equal to 0. So let's see how we can find that, okay. All right, so let me simplify this. I have, okay, did I do this right here? Let me make sure. This is 26. This is, let me see. Here I have, yeah, that's correct. So let's see. All right, watch me if there are any errors made here. So this is going to be 4 over 3 or 4 over 3. Okay, so let's see. You have 56.7 minus 0.55 f of hd, okay, minus 0.8, okay, 0.8 times 0.83. You have minus 0.66 f of hd, okay, then you have, 0.80, no, wait a minute, 0.8 divided by 0.6 times 0.83. This is 1.11, no, this is negative 1.1 f of hd. Then you have 0.8 times 20 divided by 0.6. That would be 26.6 minus 26.7 plus 26.7 is equal to 0. These two cancel out. So f of hd comes out to be, okay, 1.65. So it would be 56.7 divided 1.65 comes out to be 34.3 kilonewton. Okay,
Professor,
yes.
I think you doubled up on 26.7. It looks like you added it to 30 and then you added it again to eliminate the other 26.7.
Well, did I? So let me see here. You mean this in this one, right?
Yeah, so that should have been right before that. It should have been 30, and then the 30 would have just carried down because
So
you put the
this,
26.7 at the end again.
so this is extra, but I have it from here, right?
No. Where you put 56.7,
Oh, I see.
added 30 and
Oh, yes,
26.7.
yes. So this should be 30. Right. So you're right. So it should be 30 divided by that. So let me correct this value then. So thanks for the observation. Okay. So I have 1.30 divided by 1. Okay. 56 or no 65. 30 divided by 1.65 comes up 30 divided by 1.65 comes out to be 18.2 kilonewton. Okay, so if of HT came out to be positive, what does that mean? That means the assumed direction here is correct. So the force coming towards the joint, that means this member is in compression. So I write it next to that. Let's use the other equation. Okay. So I have, which is here, f of hf is 0.83 times 18.2 plus 20 divided by 0.6, and f of hf comes out to be, okay, 0.83 times 18.2, okay, plus 20 divided by 0.6, 58.5 kilonewton. So this also came out to be positive. That means the assumed direction here is also correct. So force coming towards the joint, that means this is also in compression. So let's see where we are now. So we found now this one and this one, right? So it's getting a little bit messy, but let's see now. We had this one. So this joint, I have 1, 2. This joint, I still have 1, 2, 3, 4. Okay, so let's go with this joint. I have only 1, 2. And it happens that, in fact, this one is the same as this reaction force. So if I find this, I've also found this reaction, although I didn't ask for it. So let's go with the free body diagram of joint D. Unfortunately, as you can see, we've run out of time, so I cannot finish this. So I will continue this next time. But one observation that I'm sure you've already made is that method of joint is very cumbersome. Lots of equations of equilibrium you write, lots of free body diagram you write. So, you know, most of the time when it comes in exam, you're not asked to find all member forces. And most of the time, that would be a problem with finding a few members, which requires you to use method of sections. But we'll talk about that next time. I'll finish this and I'll do more problems. And then on Friday, and then the next following 2 days, so which would be Monday and Wednesday of next week, we will also do, Wednesday and Friday next week, we will focus on method of sections. Any questions? If not, I have to go to a meeting and I will see you at 11:45 during my help sessions if you want to join me. Sorry about that.